Bismillahirrahmanirrahim. Mathematics HSSC-I Curriculum 2000. And from page number 28 of your textbook, that is Algebra and Trigonometry by Punjab Textbook Board Lahore. This is article 1.7 and it's part 2. The problem is to find real and imaginary parts of x1 plus iota y1 by x2 plus iota y2 whole to power n, where x2 plus iota y2 is non-zero and the values of n are plus minus 1 plus minus 2 and so on. The previous knowledge which we must have to solve this problem is that whenever we multiply a complex number a plus iota b with its conjugate, that is a minus iota b, the result is a square plus b square. That is the real part square plus the imaginary part square. Also, we know that iota square is equal to minus 1 and minus iota square will become 1. From chapter 10 of trigonometry of this, textbook, we have this result, cos alpha cos beta plus sin alpha sin beta equals to cos alpha minus beta. And also this result, sin alpha cos beta minus cos alpha sin beta equals to sin alpha minus beta. Both these results are taken from chapter 10 of trigonometry or chapter 10 of this book. Then we know the fundamental identity of trigonometry, that is sin square theta plus cos square theta equals to 1. And then we have studied in chapter 1 that the de Moivre's theorem, which is it states that cos theta plus iota sin theta whole to power n equals to cos n theta plus iota sin n theta. All these results we are going to use in the solution of this particular problem. So we start our problem. We start the solution by converting x1 plus iota y1 and then x2 plus iota y2 into their polar forms. So what are the polar forms? First, let's start. Let x1 is equal to r1 cos theta 1, y1 is equal to r1 sin theta 1. So r1 becomes square root of x1 square plus y1 square, and theta 1 becomes tan inverse y1 divided by x1. As a result, we get x1 plus iota y1 is equal to r1 cos theta 1 plus iota r1 sin theta 1. We take r1 common, cos theta 1 plus iota sin theta 1. So you can see we have converted x1 plus iota y1 to its polar form, which is r1 into cos theta 1 plus iota sin theta 1. Similarly, we will convert x2 plus iota y2 into its polar form. So let x2 is equal to r2 cos theta 2, y2 equals to r2 sin theta 2. We will get r2 equals to x2 square plus y2 square. Theta 2 will become tan inverse y2 by x2. As a result, we will get x2 plus iota y2 into polar form, that is x2 plus iota y2 will become r2 cos theta 2 plus iota sin theta 2, while r2 is common. So we get both these complex numbers into their polar forms. Now consider the result, that is x1 plus iota y1 by x2 plus iota y2 whole to power n, and put the polar forms in here. We get r1 cos theta 1 plus iota sin theta 1 divided by r2 cos theta 2 plus iota sin theta 2. And then we put the bracket around these and we take power n. Let's apply this power n. We will get r1 to power n, r2 to power n, cos theta 1 plus iota sine theta 1 whole to power n divided by cos theta 2 plus iota sine theta 2 whole raised to power n. And now we will apply the De Moivre's theorem upon it. You can see De Moivre's theorem does that. It will bring this n over here. Just like that, cos theta plus iota sine theta to power n is cos n theta plus iota sine n theta. So I'm going to get here r1n, r2n, it will remain the same. And this, by the application of De Moivre's theorem, it will become cos n theta 1 plus iota sine n theta 1 divided by cos n theta 2 plus iota sine n theta 2. And that's it. We have applied the De Moivre's theorem. Now in the next step, we are going to multiply the denominator by its conjugate, that is cos of n theta 2 minus iota sine of n theta 2. That is, we get r1n by r2n equal into the result. I must have an equals to sign here. Cos of n theta 1 plus iota sine of n theta 1 divided by cos of n theta 2 plus iota sine of n theta 2, and we are going to multiply the denominator by its conjugate, that is cos of n theta 2 minus sine of n theta 2, of course with iota, divided by cos of n theta 2 minus iota sine of n theta 2. Now how we are going to perform this multiplication? Let's have a look at it. First of all, I'm going to multiply these two. First of all, I will do this multiplication. Then in the next step, I will do the orange multiplication. That is it. After this, I will write the, let me use a purple color for it. I will write these two, and then I will write the last. In the last, I'm going to write with the pink one. Let's say I will write these two. So I'm just going to follow this plan. I have to multiply the numerator and then multiply the denominator. So to multiply the numerator, I'm going to do in this way. This multiplied by this, that is blue. I'll follow the light blue line. Then I'll follow the orange line. Then I'll follow the purple line, and then I'll follow the pink line. Let's perform this multiplication. And here it is. I get r1 to power n as it is, r2 to power n as it is, cos n theta 1 into cos n theta 2 will become cos n theta 1, cos n theta 2. Then I'm going to multiply these two. So iota and minus. It becomes minus iota square. And we have discussed before that minus iota square is plus. So I get a plus sign, sin n theta 1 and sin n theta 2. Sin n theta 1 and sin n theta 2. These are not two n's. In fact, this n is from sin. Then I am going to write this result, iota sin n theta 1 cos n theta 2. A positive sign, then iota sin n theta 1 cos n theta 2. Then I'm going to write this result, cos n theta 1 into sin n theta 2 with minus iota. So I'm going to take iota common, and I'm going to put a negative sign here. And the result will be cos of n theta 1 sin of n theta 2. And then I need a line here for fraction. Here it is. And then denominator. Well, let's see the denominator. What is the denominator here? Cos of n theta 2 cos of n theta 2 plus iota minus iota sin of n theta 2 sin of n theta 2. So it is simply a plus b, a plus iota b into a minus iota b. So the result will be a square plus b square. In place of a, I have cos of n theta 2 square plus sine of n theta 2 square. So this I get in the denominator. What results I have used here is that perform multiplication. You can do this multiplication in rough work and then find these results and put it there. I have just used this plan. First of all, the light blue line, then the orange line, then the purple line, and then the pink line. I have followed this plan and I have written it in one step here. If you don't like it, you may go to rough work, perform this multiplication and find this result, arrange it and put it here. And in the denominator, this is simply a plus iota b, a minus iota b. So the answer must be a square plus b square. In place of a, I have cos of n theta 2, and in place of b, I have sine of n theta 2. So this is it. Now we compare these results with what we have studied here. Here it is. Cos alpha cos beta plus sin alpha sin beta. It is equal to cos alpha minus beta, and sin alpha cos beta minus cos alpha sin beta equals to sin of alpha minus beta. So let's come here and we get R1n, R2n equals to cos of n theta 1 minus n theta 2. Cos n theta 1, cos n theta 2 plus sin n theta 1, sin n theta will become, n theta 2 will become cos of n theta 1 minus n theta 2 by the application of this result. After this, let's apply the second result and we will get sin of n theta 1 minus n theta 2. Sin n theta 1 cos n theta 2 minus cos n theta 1 sin n theta 2 will become sin n theta 1 minus n theta 2 by the application of this result. And in the denominator, we are going to apply this result. Sin square theta plus cos square theta equals to 1. So cos n theta square, n theta 2 square plus sin n theta 2 square, it will also become 1. So I'm going to write 1 here. Here it is. After this, take n common from this bracket and n common from this bracket, and we get it equals to R1n by R2n cos of n theta 1 minus theta 2 plus iota sin of n theta 1 minus theta 2 and a bracket around it. And now I'm going to write it in separate real and imaginary parts, and it becomes R1n by R2n cos of n theta 1 minus theta 2 plus iota R1n by R2n sin of n theta 1 minus theta 2. Result, the real part is R1n, R2n cos of n theta 1 minus theta 2, and the imaginary part is R1n, R2n sin of n theta 1 minus theta 2, and that completes our solution.